Hi guys, welcome to the home of fun and learning official. Today in this video, we'll be starting with Algebra course 1, introducing polynomials. So let's get started. So basically, what is a polynomial? When we look at the word polynomial, we can see that poly means many and nomial means terms. So we can say a polynomial is a collection of many terms. Simple, right? Okay, let's move on to the parts of a term of a polynomial, the components of a term of a polynomial. So the first component is a variable. Now, what's a variable? A variable is anything that can occupy a real value. For example, A, B, C, X, P, Q, etc. They all are variables because they can be replaced by a real value. The second component of a term of a polynomial is an exponent, which is the power of a variable or a constant. For example, a to the power 2, b to the power 3, 9.5 to the power 1, x to the power 0, p to the power 9, 33 to the power 200, and etc. And the third component is a coefficient or a constant. That is any real number that's next to a variable, which means that is multiplied by a variable. That is defined as a coefficient or a constant. For example, 3x to the power 2, 0.09y to the power 3, 4.4 to the power 0.5 multiplied by a to the power 9. Okay, all the terms that are all the things that are written with the green are coefficients and constants. Now let's move on to the rules that define a polynomial. Okay, that make us differentiate between a polynomial and a non-polynomial. So the first rule is that there needs to be a minimum of two terms, as the name suggests, right? Poly means many. Many is something that's greater than one. So there needs to be a minimum of two terms, and there cannot be an infinite number of terms, because then it would become a series, and the series, the sum of a series and sum to infinity, that's a totally different thing. Okay, you don't want that. So this is the first rule. Now the second rule is that the original domain of a polynomial must be all real values. So if you have a polynomial in, for let's say, a variable x, then x should be all real values. Okay, x can be any real value. That should be an original domain of a polynomial. The third rule is that all the exponents of the variables need to be 0 or positive integers only. That's pretty straightforward. And the fourth rule is that an expression is a polynomial only when its graph is a continuous graph. That means if you trace the graph of a polynomial, you should be able to do that without lifting your pencil or pen up. That means that you should be able to trace the graph in one go. Okay, And using this rule, using this fourth rule, we can derive one more sub rule, and that is that there cannot be a term that is divided by another term that is a variable, right? Because that just makes a rational function, right? If you have a polynomial and you divide it by a polynomial, that's just a rational function, and we are not going into that. Okay, so that's not a polynomial. A rational function is not a polynomial. So there cannot be a term. A term can be a constant. Okay, if you also divide a constant by another term, that also create discontinuities in your graph. I will explain later what I mean by that. Okay, so if all the four rules that are mentioned above are true in an expression, then you can call it a polynomial. And we have a special case here. Okay, it sounds weird, and some people accept this and some do not accept this, but let's just learn this. Okay, we have a constant polynomial. Now what is that? It is a polynomial having only a constant term. For example, 7x to the power 0, 5y to the power 0, and 45, and etc. Okay, basically a constant, right? You can also call it a polynomial, but technically polynomial is itself a thing that should have two terms, right? But some people accept this as a polynomial too, so I thought I will teach this also. Okay, now we will look at the example graphs of polynomials. Okay, and see how the graphs of polynomials look like, and they follow all the four rules. Okay, so this the 3x to the power 4 plus 7x squared plus x plus 21, this is a polynomial. It follows all the above mentioned rules, and its graph, you can also see it's a continuous graph. You can trace it using a pencil or a pen without lifting it up, so that follows all the rules. Okay, now the second graph of a polynomial, it's this: a cubic 3x cubed plus 7x squared plus x plus 21. That's also pretty straightforward. It follows all the rules, all the above mentioned rules, and the graph is also continuous graph. Okay, now here comes the interesting part. We are gonna see the example graphs of non-polynomials. Okay, so let's just see, and we will also explain why they are classified as non-polynomials. Okay, so the first graph is x to the power half. Okay, so the first rule, let's see our first rule. Okay, the first rule is that it should have a minimum of two terms, right? So it has a minimum of two terms if you look at that. Okay, because it may not seem like two terms, but look at this: x to the power 0.5 plus 0, right? This is also 0, although it's not shown, but this is two terms. This is the first term and this is the second term, so it pretty much follows the first rule. Okay, it follows the first rule. Now the second rule states that the original domain of a polynomial should be all real values. Here it isn't followed, right? Because the domain of this thing is all positive values of x only. That's a restricted domain. That's not all real values. So the second rule is not followed. And similarly, the third rule is not followed because this exponent has is 0.5, and it's supposed to be a positive integer or 0. Okay, so the third rule is also not followed, but the fourth rule is followed because you can still trace this in one go, like right, like this. You can still trace this at one go, but it doesn't follow all the four rules, so it's not a polynomial. Now let's look at another example. This, that is x to the power negative 3 over 2 plus 5x squared minus 89. Okay, that's not a polynomial, and we'll see why it's not a polynomial. The first rule, it follows the first rule. Okay, that's pretty straightforward. The second rule, it doesn't follow the second rule. Why? Because its domain is again all positive values of x only, but we need all real values. Okay, so the second rule is not followed. Similarly, the third rule is also not followed because we have exponents that are not positive integers, like this. Okay, this is an exponent that's not a positive integer. But the fourth rule is again followed. You see, the fourth rule is followed here, because you can still do this continuously, right? You can still trace this graph with a one go. Okay, and then it continues going upwards and upwards. Okay, let's look at this third and the last example. Okay, now this is a rational function because it has a polynomial that's divided by another polynomial. Okay, it's x squared plus 2x minus 3 over 5x minus 9. Okay, let's look at all the rules. It follows the first rule because it has more than one term, so yes. And the second rule, it doesn't follow the second rule because it has asymptotes. It has one asymptote at x equals to 9 over 5, right? It is an asymptote at x equals to 9 over 5, like this. Okay, this is an asymptote. So not all values of x, not all real values are the domain, so the second rule is not followed. And the third rule is followed because we have all the exponents that are positive integers or 0, right? But you see, the fourth rule is not followed. This is because you cannot trace this graph in one go. You have to lift your pencil up, then trace this second portion of the graph, or vice versa. So this rule is not followed. And just for your information, it also has an oblique asymptote at this, right? And we will come to that later on when we will learn about the rational functions and sketching of rational functions. Okay, now let's do some self practice. Okay, so here we need to identify if these are polynomials or non-polynomials. Okay, the first one is pretty straightforward. It's a polynomial. Okay, the second one is not a polynomial because it has an exponent that has a negative power. That's a variable that is a negative power, and exponent is negative. Okay, so that's not a polynomial. This is a polynomial. This is a special case, and that's a constant polynomial. Okay, constant polynomial. Some people say there's no such thing as constant polynomials, but we will follow this. If you do not want to abide by this constant polynomial thing, it's okay. Okay, it's not a rule for everyone. Okay, now 17 minus 5. Okay, it's basically 12. Okay, that's also a polynomial by this same logic. Okay, this is a very interesting question. Now at first it may seem like there's a radical, So you may like call this a non-polynomial, but that's not a case, because this radical only applies to 2, right? It doesn't applies to the variable. So this is a polynomial. It follows all the rules. Okay, now this is also a polynomial. This is pretty straightforward. This is not a polynomial because we have an exponent that's not a positive integer. So that's not a polynomial. This is obviously not a polynomial, as we saw above. It's a rational function, so it's not a polynomial. It has asymptotes and discontinuities in the graph, so it's not a polynomial. And this, okay, let's look at these last two. This is a polynomial. This is not a polynomial, because although we have this radical applying only to 9.1, but look at this is being applied to x, which is a variable, so that is not a polynomial. That's it for today. Thanks for watching. Please like, share and subscribe. We will meet in the next video. Till then, take care.